This PhysCast will look at an example of calculating nuclear decay. Pause the video to read through the question carefully. Let's begin our solution with an interpret step, where we will see quite clearly by what's given here. We've got a radioactive material, so we're going to be concerned with radioactive decay. We're told something about a change in the activity of the material, so we need to make sure we know that activity here refers essentially to the decay rate, how rapidly this material is decaying, and that's changing, and it's going to be concerned with the description of a material in terms of a half-life. So with all of these terms, what the question is really asking us to do is to calculate a time for a particular change in activity. For the develop stage, often we'll draw a diagram, but that's not so appropriate for this type of problem. So here we might recall that one of the descriptions we know for radioactive decay has to do with the amount of material N at some time t, and it depends upon the amount of material we had at time 0, so the initial amount, multiplied by some factor which we could write as 2 to the power of minus t over t a half, where t a half is the half-life. So as time increases, this 2 to the negative power becomes a smaller and smaller number. The amount we have left at that time gets less and less. Of course, the question is asking us about activity, so we need to also recall that the activity, which remember we could write as, say, the rate of change, dN dt, of our material, is proportional to the quantity of the radioactive material. So we could think of this decay equation here as well as being in terms of the amount. We can think of it in terms of, for example, the decay rate, the activity at some time t, will be what was the activity at some initial time, t equals 0, again multiplied by this factor 2 to the minus t over the half-life. And so we should be able to do something with this expression here to calculate a time. So let's move on to the evaluate stage to do that. We can probably write this now in terms of some of the numbers we have already, because this dN dt is not so easy to write down. So we should be able to write that our activity, our decay rate at some time t, which is 110 by 10 to the power of 6 becquerels, we're told, divided by that initial activity, which is 300 by 10 to the power of 6, that should equal this quantity here, 2 to the minus t over t a half. Now with this expression, one thing you might immediately think you can do, because we've got a power law on the right hand side of this equation, is if we took the log base 2 of both sides of this equation, say here of 110 divided by 300, where here I've simply cancelled those factors of 10 to the power of 6, that would equal the log base 2 of the other side of the equation, 2 to the minus t over t a half. And that's correct, but the difficulty for most of us is we don't have a calculator or any easy way of calculating the log base 2 of something. Of course, the log base 2 of this right-hand side, the log is basically the inverse operation to taking a power, and so this would just be minus t over t a half. So that would be a kind of nice way to do it, but more straightforwardly what we can do is, rather than using a log base 2, is we can actually use the log to any base, and a nice one that we can usually do is the natural log, or the log base e, of this 110 over 300 must also equal the natural log of the other side of the equation, that is 2 to the minus t over t a half. And then we can use our understanding of logs, that the log of something raised to a power is simply the power, in this case minus t over t a half, times the log of 2. And so this is a nicer expression in terms of actually doing a calculation, because we typically have a calculator that enables us to find the natural log. And we could do the same thing with log base 10 if you prefer. Of course we could do it with log base 2 if we had a calculator for which that was easy to do. So rearranging this last expression here, which shouldn't involve too much algebra, I can make t the subject of that formula. I'm going to basically divide both sides by the log of 2, so I'll have the natural log of 110 over 300 divided by the natural log of 2. There's a negative sign that I need here, and then I'm going to multiply both sides by the half-life. And my half-life in this case, the question tells me, is 20.4 minutes. So if I just plug in into my calculator to find the log of this fraction here divided by the log of 2, take the negative of that, multiply by 20.4, I wind up with an answer here of 29.5 minutes. So by my calculation, that's the answer to how long it took from delivery to actually using this radioactive material in a PET scan. It took just a bit less than half an hour, 29.5 minutes. Let's give ourselves a bit of extra space here to do an assess step. And in our assess step, we might consider that we know we began with an activity of 300 by 10 to the power of 6 becquerels, and we know that after one half-life, that would have reduced to half, to 150. And we wanted 110, so it was going to be more than one half-life. We know after another half-life, this also reduces by a half, so it would be down at 75. Of course, the answer we were looking for was, the activity we wanted was 110 by 10 to the 6 becquerels. So it's going to be something more than a half-life, something less than 2 half-lives. Our half-life was 20.4 minutes, so something more than 20 minutes, something less than 40 minutes. And indeed our answer seems to fall into that range. So we've got some confidence that we might have calculated the correct answer. And just before I finish with this particular example, I want to emphasize something here that I want to make sure that you don't do when you approach a problem of this kind, and that is that you should not be using the idea of a linear interpolation, which is often a tempting thing to do to make maybe an easier calculation. Do not do linear interpolation. I'll just give you a quick example of how that doesn't work. In this example here, you might think the first half-life, 20.4 minutes. The second half-life, we don't want all of that because we don't want to get down to 75 by 10 to the power of 6 becquerels. So that second half-life would reduce from 150 to 75 by 75. But we only want to go down by 40 to get from 150 to 110. So we might think we only need 40 out of 75, that fraction of a half-life. That would be how much extra we need. If you do that calculation there with a half-life of 20.4 minutes, you wind up with 10.9 minutes. And so with that first half-life of 20.4 minutes and this fraction of the second half-life, you add those together and you get a total time of 31.3 minutes, which is wrong. It's not the correct answer. The correct answer we know is 29.5. And the reason it's wrong is because we've used linear interpolation on a relationship that is not linear. This is a power law, essentially some kind of exponential type function. And so our linear interpolation, thinking what fraction of a half-life do we need, that's the fraction of the change that we were looking for, is completely incorrect, and you really must make sure you avoid approaching the problem using that idea of kind of some fractional linear interpolation. It won't give you the right answer. It'll give you something close quite often, but if you're asked to calculate a quantity, you don't want an estimate or something that's close, you want the exact value.